Thank you, Sunshine, and thank you for the invitation to be here. Thank you to all of you for coming. I wish the fact that I work for an organization dedicated to communication was a guarantee that I'm a good communicator. We will see. But my job today is to introduce you to climate models. And I'm not a climate modeler, I'm a statistician, but there are a lot of good climate modelers at NCAR where I work, and some of them are listed there because I've pillaged some of their presentations to talk to you about climate models. And then Reto Knuti is a friend and colleague of mine that works in Zurich, with which I've worked a lot on the interpretation of climate model output, especially when it comes to future projections. So, the idea for the presentation is I'm going to tell you about, actually right now we call them Earth system models because we are introducing processes that have to do with the carbon cycle and vegetation. And so instead of just calling them climate models, we make the jump to call them Earth system models. So what they look like, how we use them. I'm going to talk mainly about future projections, but I also want to mention stuff about observed climate. And I'm a statistician, so I'm going to focus, I hope, on the uncertainties that challenge our interpretation of climate model output. By the end of this talk, I hope I can give you an idea of what we trust about climate model output and what is more challenging to be confident about. So that's the plan, and we'll see where we go. So what does climate models look like? Well, they may look like this. And I'm a statistician, so don't ask me what's up there, but I know that's the kind of stuff that gets into climate models. And let's, to be less funny about it, the climate models are based on the laws of physics, thermodynamics, chemistry, and now even biology, because we think about how vegetation and organisms in the ocean react with carbon, for example. Some of those laws have been known and haven't changed since the beginning of the 20th century. The equations that represent those laws are put in forms that can be ingested and crunched on our computer systems. And magically, out of these things come out physical processes like temperature, precipitation, radiation, vegetation dynamics, transfers of heat between the surface and the atmosphere, or between the ocean and the atmosphere, all sorts of wonderful things. Now, some people look at climate models and see this kind of stuff. So this is computer code, and if I show you the NCAR climate model, it's millions of lines that look like that. Or it looks like this. Now, this is the computer, the supercomputer in Wyoming that NCAR uses. And this gives you an idea of how costly and complex these climate models are. So when you look at that, you realize that not everybody can run a climate model. And in fact, there are maybe 15, 20 research centers around the world that can afford to develop and run climate models. NCAR is one of those. There are a couple more in the US, like GFDL down the road in Princeton, GIS in New York. But these are really, amazing feats, and it's kind of a blessing and a curse because, as you'll understand with the rest of my talk, one of the challenges is to make sense of these models when you compare them to one another. And it's not the kind of enterprise that you can address by sitting at your desk and running little simulation and perturbation and compare what comes out of these analyses. You need a lot of time, a lot of computing resources. Anyway, the idea of a climate model is really to be a surrogate of our planet. And the way it does that is by discretizing both, the surface, the depth of the ocean, the height of the atmosphere into these regular grids. And then at each point in that grid, those laws act, and what happens at time t gets propagated to the nearby cells at time t plus 1, and so on and so forth. Now, in each of those cells, all sorts of things happen. So you have winds, you have salinity in the ocean, you have snow cover, you have precipitation, you have clouds. So you get a sense of the complexity of this stuff. Now, as you can imagine, or maybe I haven't told you, but the figure in the previous slide should have given you an idea. These things, these cells are pretty large. Like right now, you know, if you're lucky, you get 25 kilometers in size for one of those cells in the horizontal domain. But it's more typical to have on the order of 100 kilometers in size. So if you think of a cloud, especially a thunderstorm cloud, you realize it's much smaller than that. And that suggests that climate models cannot really represent everything exactly. They have to approximate things, and that's where uncertainty comes from, and that's where the difference between the climate model at NCAR and the climate model at GFDL comes up, because the way the scientists that have developed the NCAR climate model have chosen to represent those processes that they cannot simulate exactly in a certain way, which is based in scientific understanding and observations as much as the way that the GFDL model is doing it. But they may choose some value for those parameters that is, you know, slightly different, still justified. But unfortunately, those changes in parameters make our simulation of the future different from model to model, and that's where a lot of the uncertainty comes from. I have this wire that falls, but I hope you can hear me anyway. As I said, one of the ways climate models evolve is to include more processes, and I mentioned that one of the newest direction of development is to include things like you see on these slides. Vegetation dynamics, the way vegetation grows, reacts to the availability of nutrients, for example, carbon dioxide. The way, you know, the surface that is covered by a forest reflects more or less sunshine than a surface that is, for example, a savanna or cemented surface. Certain models actually simulate urban canyons so that the famous urban heat island can be assessed and simulated. In general, climate models evolve by including more and more processes in their representation. Okay, so now after all these words, I want to show you something nice, which is another way to see what a climate model looks like. And so this is a movie of the output of the NCAR climate model run, I think, at 25 kilometers resolution. This is water vapor, and if you look you know, around the tropical oceans, you see the formation of hurricanes. Now, if I showed you the equivalent climate model of 5 years ago, that would have been probably at 250 by 250 kilometers in resolution, and there would be no way that we could see the formation of hurricanes, because just the wind speed at that resolution is not high enough. And those hurricanes came up just by making the resolution finer, applying the same laws, the same code, but now all of a sudden you have the emergence of a process that just by, you know, being resolved enough is present, and it was not. Nobody went in and, you know, seeded those hurricanes by hand. They just came up. So that's a pretty neat thing, I think, especially for a statistician like me that doesn't understand exactly how these things work. I'm sorry?
What data did you use to drive these?
Well, so one of the things that I probably should get at is that these models can run in isolation. You start them from some initial conditions, and then the laws of physics and thermodynamics act, there is no tweaking, no data that goes into this simulation as they run, except you can use so-called external forcing, which is what we use to see what, for example, the increase in greenhouse gases are going to happen. So there are external perturbations that we can impose. For example, increase in greenhouse gases, for example, changes in the solar cycle, for example, volcano eruptions. These are so-called external forcings that change the evolution of the climate system. But you can run a model like this, as I said, in isolation of external forcing, and everything that you see comes up. Now, another representation is this one, where you now see the currents in the ocean. And just as a little bow to the institute that is hosting me. So again, pretty neat stuff. You see actually the. Do I have a pointer? That's okay. Don't worry. I don't even like to use pointer. I can use my little hand. Don't worry. No, that's okay. I prefer the little hand. So you see here the Gulf current, and there is a similar one around Japan, and you see the westerly propagation here in the tropical ocean. Okay, so what are these climate models? Well, one way to think about it is a virtual laboratory. As I said, these are surrogate of the planet Earth, and you can use them to try and answer a lot of questions that you may have. One of the questions we like when we think about global change and future global change is a what-if question. What happens if I increase greenhouse gases? We may be interested in mechanisms even if we don't care about global change. We may be interested in simply studying, El Niño, La Niña processes. These models are useful for that. We want to maybe analyze the interaction of different components, how the ocean reacts with the atmosphere if I, perturb it somehow. But for somebody like me, and probably somebody like many of you, one of the most compelling questions nowadays is to try and assess how the climate system is going to react to this major external forcing that we are imposing, which is the increase in greenhouse gases. And so when it comes to predicting future behavior, these are the tools we use, because these are really the only tools that are available to us for scenarios where the perturbation is so big that we cannot really use the past to say something about the future. The extrapolation by itself would be too big. The ultimate goal is to understand the climate system. And I was talking to somebody here in the audience. I think this is a great thing, but it's also what makes the assessment of these models really tricky, because usually, at least if I think of myself as a statistician, or I think there are a lot of domains in life where you build a model for a very specific purpose, and you can assess the validity of that model, and you're willing to tweak that model to address that particular questions. These things are made to answer a lot of different questions. And so the assessment and the tuning that you may want to do would screw up something else than the thing that you are particularly interested in. Oh, thank you. Of course, I'll never use it for the rest of the talk, but I'll do it right now. So that's really a challenge, because these are kind of multi-purpose tools, and I may be interested in using them to answer a certain question, and you may be interested in answering another question. So the model has to be good at both of them, and I cannot tweak it in my direction without challenging you. Okay, so why do we trust, though, these models? Well, these models are run over the current period as well as the future. So over the current period, we actually have observations, and we can compare what comes out of this model. So here are a couple of examples of things that come out of these models, and we can assess Of course, these are not weather models, so they're not supposed to tell you exactly what happened on a specific date of a specific year. They are used to look at statistics, and that's why I have a job in this area, statistics of the climate. So in this case, for example, this is a representation of Arctic sea ice cover on a specific month, March. And on this panel, we have observations, and these are averaged over a certain number of years. So this is an average behavior of the sea ice in March. And this is the average behavior from the NCAR model, trying to approximate the statistics that you see on this panel. And so people go in and look at this closely and decide that the model is good, and it may have a certain bias in certain areas, but all in all, it's doing a good job in representing what we know of the behavior of sea ice in March over the Arctic. There are even more complex things that people look at, and you can tell that I've used some of the slides of somebody that works in the Arctic, because this is Greenland, of course. And this is a representation of ice melting velocity over Greenland. And again, you have observations, and you have the results of a 5-kilometer resolution model over Greenland. And again, if you compare the different velocities that have to do, of course, with how the terrain is shaped or how close to the edge of the water you are, you can decide that the model is fairly precise or fairly accurate in replicating this behavior. You can use the model to look at, again, the behavior of El Niño or La Niña, and again, you have observations over a certain period. You can compare what happens in the model. You can assess, the strength of El Niño and La Niña events. You can compare them to observation. You can look at the frequency with which they happen and compare them to observation. And so again, we look at these models and we decide that they are, acceptable for the representation of these processes. And as you can imagine, the community of scientists that look at this model is humongous, so they are looking at each and every aspect that you can think of: ocean, ice, land, atmosphere. Anything that comes out of the model and that can be observed is going to be assessed. Now, how do we use these models for stuff related to climate change? Well, one way we use them is actually to look at past changes and try to decide if these past changes are attributable to human causes. Not everything that changes in the past can straightforwardly be blamed on our carbon emissions, but some things can. And for example, you look at the record of global average temperature. In black here are observations, and underneath you have again the NCAR climate model simulating average temperature over the same period with a lot of different trajectory, because you can perturb the initial conditions, and since the climate system is chaotic, you get a slightly different trajectory, but the statistics of the trajectory should be similar to what you see in reality. Now, this is simulations where people have imposed the changes in CO2 as they were observed. So those external forcings that we were talking about in these simulations are recreating what we know of the increase in greenhouse gases that we have observed. Now, we can do the same with the same model without imposing these changes in greenhouse gases. And this is the result in blue, and the black line is the same as above. And you see that without imposing the change in greenhouse gases in the atmosphere, the behavior of global average temperature coming out of this model is much different. It stays much flatter. You don't have the increase that you see here. So this is a way where climate scientists can actually play around with the system and conduct these experiments that are almost like what you do in, with rats in a laboratory, where you have rats exposed to a treatment and rats that are not, and then you compare what happens. Here you are taking the earth and exposing it to the treatment that we are exposing it to, and we take another earth the model, another model, or another version of the model, where we don't apply the treatment, and we see the differences. And then we compute statistics, and we find that this simulation is much more coherent with what we know. I'm already at halfway. Okay, I have 21 here, so yeah, you're... Okay, so now my job has been mostly to use climate models to talk about climate predictions, so future. And I always say it's kind of a convenient thing to do because I like to talk about the end of the century and I'll be gone by then, so I may be wrong and nobody is going to come and get me. But anyway, so the first thing I want to note here is that this is a really fundamentally different problem than predicting weather. So we are applying a change in this external forcing. Mainly is this large increase in greenhouse gases that we have already started and is going to continue if we don't do anything about it. And given that the forcing is very large and very predictable, or at least you can make scenarios that are realistic of future emissions, we know that the changes in the system are going to be predictable. But I'm not going to tell you, as you know, exactly what's going to happen on a certain date in the future. I'm going to tell you something about the statistics of the climate in the future. So again, I'm not going to tell you the temperature in Rhode Island on a certain day in 2050. Actually, not even next year, as you know, I can do that. But I'm going to tell you something about the general behavior of the climate system. In particular, in this case, I can tell you that the temperature is going to be warmer on average in 2050. So this is kind of an obvious and trivial example. Climate models help us understand much more of the changes that are in store. So, for example, again, they can tell me something about Arctic sea ice behavior under increased greenhouse gases. They can tell me something about how the globe is going to warm, and not only in general that it's going to be warmer, but it can tell me something about the spatial patterns of that warming. And they can also tell me something about extreme behavior, changes in heat waves, for example, or precipitation extremes. And so, for example, again, using the NCAR model, I can tell you that this is the prediction for Arctic sea ice extent under a certain scenario of greenhouse gas increases, where by the second half of this century, Arctic sea ice will have mostly disappeared, at least in September, which is the time when it's at its minimum. But I can also tell you something about how the globe is going to warm. And these are three different projections depending on assumptions of greenhouse gas increase. So I may have an optimistic scenario where we get it together and we curb our emissions. And so by the end of the century, the warming is only at these levels. I can have a medium emission scenario, slightly more pessimistic, or a very pessimistic one. And the different colors here, even if you cannot read it, are changes in temperature, with the purple being upward of, I don't know, let's say 10 degrees or something. Similar stories for statistics like heat wave intensity, where depending on the scenario, I can have large or small changes. And I can do the same for precipitation and show you changes in precipitation under a low scenario of emissions or a high scenario. And these are different dates in the future. And the colors indicate changes in percentage of precipitation. Let me skip ahead because I want to get to something a little less Pollyannish, which is, so far I told you, that climate models are these tools that provide you with a sandbox, really, to test your theories and assess the behavior of the system. And I told you that when we run them for past and current climate, we have all this wealth of observations. We can test their performance. We can decide if they are adequate or not. We can try to improve them. And when we run them for the future, we see a lot of interesting changes, not very good ones, but we have a very good representation of those changes. Okay, so this is all good, and if I stopped here, we would all go home and be very happy with our climate models, but I wouldn't have a job. So I want to go on and talk to you about uncertainties, and uncertainties are very uncomfortable, because it's no longer the case that these climate models are just used in the scientific community to, please the intellectual curiosity of scientists. More and more, they are asked to provide information to decide on things like mitigation or adaptation, and when it comes to communicate these findings to the public, you want to be sure to have robust messages to characterize the uncertainty of these messages in a fair way. And so that's where the can of worms opens up. So I told you that there are different models in the world, and I hinted to the fact that different approximations made within the model, different choices of parameters, different structural choices. Like the NCAR model, decides to include vegetation and urban canyon. Maybe the GFDL model doesn't. That affects not only what happens right there on top of the urban island, but affects climate in other places. So the differences will be significant coming out of these models. And there are models all over the world. They all make slightly different choices, and we are left with the problem of reconciling their responses to these changes that we impose and communicate them. There are also other kinds of uncertainties that are more inherent and inescapable. So future emissions, these have to do with the behavior of society. We are not, that I know, the deterministic system. So we can make up a lot of realistic stories on how international cooperation, technology, economy, population are going to change in the future. And these different assumptions will change the trajectory of greenhouse gases that are going to go up in our atmosphere and stay there. So future emission scenarios are a source of uncertainty. And then, as I said, the climate system is chaotic. So I will never be able to get rid of that noise in the system that makes the weather unpredictable after a week or a month. So again, I can make statistics, and if I perturb the system, I'll have a response that on average I can predict. But if I'm interested in more, time-specific aspects, there will always be that noise there that I have to negotiate. And so there are these three sources of uncertainty: model structure, internal variability, and there is that Lorentz system there to remind you of the chaoticity of the system, and the future of our economic and technological and demographic development. And let me skip this slide. I just want to touch upon these different sources of uncertainty: model, internal variability, and scenario. This slide was just to tell you that depending on what you're interested in, if you're interested in global average temperature or temperature over a specific region, or if you're interested in temperature rather than precipitation, or if you're interested in 2050 rather than 2100, those three components of variability or uncertainty have different weight. So you may be saved by the fact that if you're interested in things that are close, scenario doesn't matter, because emissions stay in the atmosphere for long enough and take time to build up. So even different trajectories in the short term don't really matter. But anyway, let me see. Sunshine, how much time? Sorry. 15. So let me go ahead. So I told you we have different models out there. Why can't we decide which one is the best? Well, there are an infinite number of metrics, like I told you, that I can apply. And it turns out that different models have different strengths, different weaknesses, but when it comes to future projections, everything is interlinked. So it's really hard to decide which model is, the winner. And not only that, but there are uncertainty in observations. So to decide that one model is better than another is really tricky if they are close. And more in general, as I said, these are models for multi-purpose questions. And so it's really hard to decide which one is the best. And the example for those of you that like to drive cars is that if you're interested in, racing on a highway, you may want that car. If you live in Colorado, you may want this. Actually, maybe not that because it's a really old one, but you get the point. And more in general, or maybe more interestingly, is that it's really hard to find an aspect of current climate behavior that is relevant for the future. Let me just go to the next slide, and I think I'll try to make it clear. So let's say I have a model, and it produces temperature for current climate. So I can actually confront that picture with observations and decide that that model is accurate there, but less accurate somewhere else. Now, that model will produce a certain warming for the future. And then I have another model, and they all do the same in the sense that they all have a certain performance that is slightly different from one another, and they all give me some warming, but it's slightly different. Okay, so I can confront those pictures there with observations, and I can determine what we call bias, which is the errors. And now here, for example, you see that this model has a very large error here, meaning that it actually has, its temperature is warmer than what we observe. This other model has the opposite. Its temperature here is cooler than we observe. But look at this. Their warming for the future is almost the same in this area. So this is just an example. It's a simplified one, but it's really the true situation where biases, errors that we can measure tell us very little about the future behavior. It's the curse of wanting the models to tell you something about the derivative when all you can measure is the state that you have right now. We haven't perturbed the system enough to gauge the reaction of the models explicitly. Another aspect that makes things a little complicated is that we have maybe 20 models, and we would like to think that if they all tell us the same thing, then we should be more confident on that thing. But it turns out that models have been developed not independently of each other. So the fact that they tell us the same thing is not an independent piece of information that we can, be confident about. So this is a picture we have in the IPCC report. In that case, we get up to 40 models, just because the NCAR model has submitted 4 versions. So it's not 40 research centers independently, but we get 40 models, all slightly different, but all saying something similar about the future. And you would like to, gather strength from the consensus here. But then if you look at how these models have developed, this is just a schematic. These are all the different models, and the colors kind of tell you that they all belong to the same families. Like there was something developed here in the 60s at UCLA, and it's the father of a lot of climate models that now have a different name. So you can imagine that you get a number of models, they all tell you the same, but it's probably because they have a lot in common, not because they are independent of each other. And now just a very small example of how internal variability creates problems. So I take the NCAR model and I run it with slightly different initial conditions. And I get, let's say I do this 10, 20, 30 times, and I look at future climate, and this is the average of what comes out over North America. So this is warming, and it's telling me that, you know, it's gonna warm more, of course, up here than down here with this certain pattern. But then I look at the individual models simulation, and all of them are as realistic as the next because they are just possible realization of a chaotic system. So I can take the warmest that comes out or the coolest that comes out, no longer the average because we won't live in the average, we will live in one of these. And you see what a difference it can make. And these are, you know, probably by the middle of the century. So projections are going to be very uncertain, even within the same model and within the same scenario. Okay, let me skip ahead. I have the same example for precipitation. Future scenarios. I already mentioned this, depending on assumptions on our future technology, you know, if we get it together, if we collaborate with the next nation, if we have a lot of population increase or not, we will have very different changes in our future emissions. So these are all the scenarios that people have come up with the last time around. And these are emissions of CO2, and these are concentrations. So this is what we do year to year, and this is what accumulates in the atmosphere. And you'll see that depending on all these assumptions, I can have something as bad as this or as good as this. And these are all considered realistic or feasible. Somebody questions the possibility that we can stay as low as here, but these models that produce these projections don't actually invoke miracles. So it's supposed to be you know, realistic enough. Okay, so I talked your ears off about uncertainties. I want to actually tell you something I don't know, positive in the sense of concrete about what we learned about this latest generation of climate models. And if I really fascinate you with this presentation, you can go online and download this volume, which is probably 2,000 pages, so it makes a good doorstopper too. And it's you can find in chapter 12 in particular future projections. So I can show you what we knew the last time around when the last IPCC was produced in 2007. So these were the projections of global average temperature increase by the end of the century under 3 scenarios. And these are the new ones. Now, the scenarios have changed, but you can tell that the envelopes there, which measure the uncertainty, have not changed very much. So, you know, we are confident about the mean expected change. We still have a lot of uncertainty, even at the global average temperature scale. But if I look at geographic patterns of change, these are the old ones, and these are the new ones. This is precipitation, this is temperature, old ones, new ones. These are temperature change per degree of global warming. This is precipitation change per degree of global warming. And if you are far enough in the audience, I challenge you to see differences between these 2 panels. And so this means that the models agree in you know, the shape of things to come. They may not agree on the absolute value of the change, but they agree on the fact that those high latitudes are going to be impacted the most, that land is going to be impacted more than the ocean, that the northern hemisphere is going to be impacted more than the southern hemisphere. And at the same, for precipitation, they know that the high latitude are going to be wetter, that these areas, especially the Mediterranean, I left Italy just in time, I guess. It's going to be very dry in the future. The tropical ocean is going to be wetter. And it was the same the last time around. So it's not that we didn't learn anything new, it's just that the basics haven't changed. And it's pretty, maybe it's obvious because it's all based on the same laws of physics and thermodynamics, and those haven't changed, but it's a good result. We understand what's going on. Now, in the interest of time, let me skip ahead and just go to the conclusion and challenges. And if there is time, I'm going to show you another movie. So what did I tell you? Well, I hope I communicated a few things. One, that models are getting better. We are improving them. We are confronting them with observations. We are adding more processes. But as I showed you just now, the spread in those projections doesn't really change, so we are not reducing the uncertainty very much. It's true, one can take the skeptical view or the pessimistic view that models are always wrong, right? I think there is a good sentence that says all models are wrong, but some are useful. So our models are always going to be wrong, but they are adequate for purpose. The problem is that that purpose is kind of a very complex one, and different people have different purposes. It starts to translate model performance that we can measure in future reliability. And models are dependent, so it's difficult to make sense of this ensemble of models. The fact that they agree is not necessarily, reason for being super confident about. And then there is that natural variability that is going to always be in the way, because that is really unpredictable. It's the butterfly effect that we cannot get rid of. But we know there are robust findings, and especially if you're interested in large-scale projections, continental scale projections, there is a lot of robustness from generation to generation of models. The patterns of change are robust. We understand why they are there, and that's important. So it's not just, blind faith in models. It's because we understand why the high latitude are going to warm more or are going to be wetter. We trust the consensus, but not, to a literal way. Like the fact that I have 20 models that agree, I'm not going to give the result 20 times as much confidence as I would if they were independent. But of course, the fact that they agree is a reassurance that the processes at play are the processes that we understand and that are at the basis of these models. As a rule of thumb, everything related to warming is more robust than everything related to how the dynamics, things moving around on the Earth, are going to change. So when you hear that the future is going to be wetter, it's true because we know that hotter air holds more moisture. Where exactly that moisture is going to be transported is much trickier to predict. But the fact that on average we are going to see more rain, it's fairly difficult to challenge. And of course, if we can look at changes and not only already see them happening and then see that the trends in the future are consistent with what we have already seen, but we understand why they are there, then that gives us more confidence than otherwise. So usually climate scientists don't blindly take the results of models and trust them. They want to understand why they are there, and they want to ask, do we already see these changes? Because we have already increased greenhouse gases, so we should already see at least the seed of what we expect for the future. So the point I want to make, and I think I mentioned before, is that all these issues are more and more relevant and critical because it's no longer the case that NCAR scientists work in that isolated castle that is NCAR, for those of you that have been in Boulder, but they are asked to provide information to people on the ground that actually have to make decisions about adapting, mitigating. And so all these issues about uncertainties, I think, become more and more relevant when you actually have to say something about the actual world and actual people and actual money at play. So let me show you, given that sunshine likes water vapor, let me just put up this movie, and I can take questions. But this is actually a movie where you will see water vapor now and water vapor in the future. And it's just a nice representation of something that we understand well, which is why water vapor is going to increase, because there is going to be more evaporation from the ocean, and the air will hold more moisture. And so it's one of those results where we feel confident, and it's a very big change. As you can see, this is the higher scenario in the future. Now, what we are not as much confident is how those things will be transported towards the higher latitude where the storm track is going to be and all that stuff. But the fact that on average we're going to be wetter, it's a fairly robust finding. So let me stop here. I hope I gave you at least, I don't know, food for thought or questions, and thank you for your attention.